This video was sponsored by KiwiCo. More about them at the end of the show. On February 15th, 2013, over Chelyabinsk, Russia, an asteroid heavier than the Eiffel Tower slammed into the atmosphere. And then, 30 kilometers above the ground, it exploded. This violent event was brighter than the sun, but so high up that it was silent for a full 90 seconds after the blast, which only made the devastation worse.
So you see all these videos. People look at what was that? They see the smoke trail in the sky. And, oh, that's amazing. And then, just when you think nothing's going to happen, the shockwave hits and it blows out the windows. 1,000 people got glass in their face, in their eyes, because they're looking through the windows.
The shockwave damaged thousands of buildings and injured 1,500 people. What makes the Chelyabinsk incident kind of embarrassing is that the very same day, scientists had predicted that an asteroid would make a close flyby of Earth. And they were right. 16 hours after Chelyabinsk, a similar-sized asteroid, known as Duende, came within 27,000 kilometers of Earth's surface. That's closer than satellites in geosynchronous orbit. But while they correctly predicted this close approach, they completely missed the unrelated asteroid that exploded over Russia. And the truth is, this happens all the time. We're really not that good at detecting asteroids before they hit us. Since 1988, over 1,200 asteroids bigger than a meter have collided with the Earth. And of those, we detected only 5 before they hit, never with more than a day of warning. With all our technology and all the telescopes across the Earth, not to mention the ones in space, why do we struggle to detect dangerous asteroids before they strike? What are the chances that a big asteroid will hit, wiping out most, if not all, life on Earth? And if we saw one coming, what could we do about it? Asteroids are the leftover debris from when our solar system formed. 4.5 billion years ago, rocks and dust clumped together into molten protoplanets. Inside, heavy elements, metals like iron, nickel, and iridium, sank into the core, leaving lighter silicate minerals on the surface. Some of these protoplanets grew into the planets we know today, but many more collided with each other, breaking into pieces. These pieces continued orbiting the sun and smashing into each other and breaking into even smaller fragments. These became the asteroids, which is why some of them are rocky, loose conglomerates of gravel-sized rocks called rubble piles, and others, from the cores of planetesimals, are mostly metal.
So this is an iron meteorite, and essentially it's the piece of a core of a small planetary body, like basically a small planet, that formed 4.5 billion years ago, differentiated, so the core material fell out, and then this thing was smashed apart by a collision with another asteroid. That's the oldest thing you'll ever see.
Most of the asteroids have stable orbits between Mars and Jupiter in the main asteroid belt, but some have made their way closer to Earth, and these are known as near-Earth objects. They are of greatest interest to us because of the threat they pose. In his last book, Stephen Hawking considered an asteroid impact to be the greatest threat to life on Earth. But finding asteroids is difficult for several reasons. Most are spotted by ground-based telescopes.
So what you do is you take a sequence of pictures, 1, 2, 3, 1, 2, 3, 4, and you look for essentially a moving dot. And it's moving because it's orbiting around the sun. whereas the stuff far away, the stars and galaxies, are not.
But you have to look carefully. Asteroids are not very big. They range from meters up to kilometers in size. And in the vast expanse of space, rocks like that just don't stand out. And even the small ones can be damaging. The Chelyabinsk meteor was only around 20 meters in diameter, roughly the width of 2 school buses. Plus, asteroids are rough and dark. They only reflect around 15% of the light that hits them. So our best chance to see them is when they're fully illuminated by the sun. And that's why over 85% of the near-Earth asteroids we've detected were found in the 45 degrees of sky directly opposite the sun. This is called the opposition effect, and it means there are likely more near-Earth and potentially hazardous asteroids that haven't been detected yet. Any asteroid approaching from the direction of the sun just can't be seen. This is exactly what happened with Chelyabinsk. So far, we have detected and cataloged 1 million asteroids, the vast majority of which are in the main asteroid belt. But 24,000 are near-Earth objects, ones that we need to keep a particularly close eye on, because even once you've detected an asteroid, it's hard to tell if it will hit the Earth.
So if you just discover an object and you only have data from a few days, then you can't really tell where it's going to go because you're trying to take this little arc of motion and predict it far into the future. So what you need is observations over years and years. But even if you have perfect observations of an asteroid, there's kind of a fundamental limit to how far in the future you can predict. And that's because a couple of effects. But one is that, they're not just orbiting the sun with no other influence. All of the planets have gravity, and all of the planets are pulling on near-Earth asteroids and can change the orbit significantly. So there is something called dynamical chaos, which basically means after a certain amount of time, you don't know where the asteroid is going to be. And in practice, what that means is we can't do any work more than 100 years in the future. So the maximum time you can predict with any accuracy at all where a body will be is about 100 years.
And this is pretty important, because we know with certainty if one does hit, the results will be dramatic. This is Barringer Crater in Arizona. It's named after mining engineer Daniel Barringer, who was the first to suggest it was formed by a meteorite impact. The prevailing view, even up until the 1950s, was that it was created by volcanic activity. But Barringer was convinced it was the site of an iron meteorite impact. So in 1903, he staked a mining claim and began drilling for the metallic meteorite, which he believed to be worth more than $1 billion 1903 dollars.
Yeah, so people are motivated by money, right? So they thought, hey, we can get some iron for free, basically. So they started to drill in the bottom of the crater and found nothing. And then they started to do other exploratory drills, and this went on for years and decades. They started to drill sideways. Somebody said, maybe it came in from an angle, which it did, and maybe the iron is not under the middle, but maybe it's over there under the wall. So he was doing drilling. If you go there, you can see the drills now. He was drilling around the wall. He found nothing. So what they didn't realize is when you have an impact at high speed, it's not like you're throwing a stone into a brick wall, and it makes a hole and sticks in there, or just bounces off. It's explosive. It's like totally explosive. So the kinetic energy of the projectile comes in maybe 30 kilometers per second. The kinetic energy of the projectile is big enough to completely vaporize the projectile. It turns it into a gas. And that gas is super hot and super high pressure. And it explodes, and it blows out the crater. So the projectile doesn't really exist.